Aloha from the great state of Hawaii. The National Space Society is proud to share with you the grand prize winning entry for its prestigious premier program, the NSS Space Settlement Contest. My name is Lynn Zielinski, and I am the NSS Vice President of Education and Outreach. For more than 25 years, thousands of students ages 12 to 18 have submitted entries either as individuals or in teams from anywhere in the world. In 2021, more than 6,800 students submitted 1,600 entries or more to the contest from 22 countries. Each year, the students constantly surprise us and amaze us with their passion, their ingenuity, creativity, and this year is no exception, as you will see. The grand prize winner receives a $5,000 scholarship from the Herman Reuben Endowment Fund. Next slide. And the Starship Crystal, which is a 3D map of stars within the 5 parsecs of our sun. With thousands of exoplanets being discovered around these kinds of stars, we can look at them as being possible habitable places for humanity to settle in. And as a result, it would exemplify the whole idea behind the NSS vision, which is for people living and working in space to benefit the humanity on Earth. So with that, I am delighted to present to you the 2021 Grand Prize winning team from Makualani Christian Academy in Kona, Hawaii. The Aerospace Meridian team and their teacher advisor, Frederick Herman.
Thank you, Lynn. We're very proud of our students, and we have our beautiful award here, a nice three-dimensional, somehow they got the stars' names engraved in here, and it's absolutely gorgeous. We're going to put it on display at the school for everyone to enjoy.
Yes, actually, this is a pair of bookends for you, I believe, because in 2019, your team also won the grand prize for another project that they did as well. And I believe 3 members of your team are still on this project. The others have graduated.
Yeah, that was the Corpus project in 2019. And Hannah, Joe, and Austin were also part of that team.
Yeah, and what's really cool and unique about your project is that you have done some experimentation with it. And unlike other projects presented in the Space Settlement Contest, the students generally just do paper and pencil, but you guys actually did experiments. And what's really amazing is that I believe Austin and Andrew, you guys actually have a patent that is given to you this year for what you developed in 2019 and augmented for this particular contest. So congratulations, Austin and Andrew.
Thank you.
Yes, it's always more fun to conduct real-life experiments than read something in a textbook.
And, you know, blowing stuff up is pretty cool.
Okay. Well, with that, I will leave the team to give their presentation to you.
Aloha, and welcome to the 2021 NSS Space Settlement Contest Grand Prize presentation. Our team is Aerospace Meridian from Makualani Christian Academy in Kailua, Kona, Hawaii, and our project is titled the ASM Venus. I would like to start off by thanking everyone at the NSS for again awarding us with such a high honor. We are truly grateful. My name is Michaela Chang, and this is our team. From top left to right, we have Austin Pham, Jackson Flegel, Andrea Olasfred, Josiah Richards, myself, Michaela Chang, Christian Tanya Memento, and Hana Husek. Our project has 3 phases. First, the construction of a ground station and transport ships. Second, transport to the asteroid 16 Psyche. And third, the construction of the ASM Venus. An imperative factor in spacefaring is being able to communicate between your space station and a home planet or base. To do this, a reliable ground station is needed. We took it upon ourselves to build a ground station because we were curious and wanted to prove we could receive signals from orbit. A simple ground station is composed of several components: an antenna, a transceiver, a rotator, a satellite tracking program, we use gpredict, and software that converts radio signals into computer code, we use SDR#. This is the ground station that the Aerospace Meridian team has built to receive signals from passing satellites. Using a Yagi antenna, a rotator, and a tripod, we built what could be called nothing less than a masterpiece. This impressive piece of technology is capable of communicating with spacecraft small and large, like CubeSats and the ISS. With the ground station complete, the crew members can focus on constructing the ASM Mercury. The Aerospace Meridian team developed a transport ship for the nearly 370 million kilometer journey from Earth to the asteroid 16 Psyche, the ASM Mercury. The ASM Mercury is a transport ship built in low Earth orbit. It will rotate in order to create artificial gravity, which will prevent the crew from the negative physical effects caused by zero gravity. These maladies include bone deterioration and muscle loss, including weakening of the heart. It will also contain bigelow spheres stacked in rows around its circumference. Why bigelow spheres? Bigelow spheres are lightweight. The surface of a bigelow sphere is not a metal alloy, but an aramid fiber similar to Kevlar. They can be shipped to space in compact form, then inflated once in place. Thus, they are both more protective than a metal alloy and less expensive to transport. We are, in fact, planning 2, not 1 Mercury-class spacecraft, the ASM Mercury 1 and the ASM Mercury 2. Why do we need 2 Mercury transport ships? Crew members can live in one transport while the other is dismantled for the early construction of the ASM Venus. I will now pass things over to Andrew Olafsrud, who will be discussing the shielding of the ASM Mercury.
Hi, I'm Andrew Olafsrud. There are several dangers for structures that are intended to exist in space long term. One such danger is high-velocity particles, also known as HVPs. The dangers of HVPs do not lie in their size, as they are extremely small. However, they tend to move at speeds upwards of 30 kilometers a second. This gives them a similar kinetic energy to a bullet. Tens of millions of HVPs are estimated to be in Earth's orbit alone. An impact with an HVP is a guarantee. In 2019, several members of the current team won the NSS Grand Prize in the Space Settlement Contest with the ASM Corpus project. To develop shielding for our current project, we looked at the previous project for inspiration. The 2019 design used a diamond corrugated shielding as the first layer of defense to deflect the HVPs and shrapnel in several directions. We identified this deflection shielding as one to be developed further. The diamond corrugated shielding was replaced with numerous hardened plastic spheroids that function on the same principle as deflection by dispersing the kinetic energy at various angles, while bouncing off each other and the walls of the shielding. We added shear thickening fluid to dampen spheroid energy. A shear thickening fluid hardens when pressure is applied to it before returning to a more fluid state. By hardening against the motion of the spheroids, the shear thickening fluid reduces kinetic energy, adding significantly to the effectiveness of the shielding. A strong material was still needed to hold the components together. We decided on using Dyneema, a strong aramid fiber, 15 times stronger than iron, but still quite flexible. Dyneema is stronger than Kevlar and is hydrophobic, meaning that it will not absorb or leak the shear thickening fluid. Dyneema is therefore used as the external shell for the shield panel. These 3 components are combined into a shield panel. When an HVP impacts a shielding panel, it will disintegrate, and its kinetic energy will transfer to the spheroids, which will collide with each other, resulting in a chain reaction that absorbs the kinetic energy. The shear thickening fluid will harden against the spheroids, dampening their motion. Our invention also allows for self-healing. When a puncture occurs, the spheroids will be drawn to the hole by the vacuum pressure of space. blocking the hole and reinforcing the damaged area. We decided on the sizes of these spheroids to vary with a precise amount, such that a spheroid one size smaller can fit through the gap of one size larger. This will ensure that the self-healing will always function at full efficiency. We tested our invention using a high-powered rifle. While we were not able to produce a full prototype, we were able to test the proof of concept by using configurations of aramid fibers, spheroids, and a shear thickening fluid. The test demonstrated that the spheroids, aramid fiber, and the shear thickening fluid were able to effectively stop and deflect the bullet. With full shielding, the test results showed only an entrance hole, but no exit holes. Testing variants such as the shear thickening fluid without the spheroids or spheroids without the shear thickening fluid resulted in significantly more damage. The conclusion to these experiments was that Dyneema, spheroids, and shear thickening fluid was the optimal design. After the success of the testing, we decided to file a patent for the invention. The patent application, we were fortunate enough to have a patent lawyer offer to do work pro bono, and our patent will be published this year. Our final shield panel design uses Dyneema, hardened plastic spheroids, and polyethylene glycol with suspended silica particles. Our design can easily be applied to Bigelow spheres. Thus, the ASM Mercury will be protected while in low Earth orbit and during transit to 16 Psyche. Now, though we have a shielded transport, we will need to move it to 16 Psyche. We will be using Hohmann transfers. Furthermore, we will also need to address the language transition for the multinational crew. Hanna Husek will be describing our plans.
Hi, my name is Hanna Husek, and I will be discussing Hohmann transfer and language education. The Mercury will initiate its transfer orbit with a prograde burn. This will move it into an elliptical orbit around the Sun with a periapsis at the Earth and an apoapsis intersecting with the periapsis of 16 Psyche's orbit. Our teammate Jackson Flegel calculated that a prograde burn of 5.81 kilometers per second will be needed to achieve the desired transfer orbit. Unity is developed through communication. But how will ASM crew members communicate if they're from 10 different countries and use 10 different languages? In the isolation of space, crew members will need to overcome language barriers. It is helpful for crew members to be aware of what happens when people learn foreign languages. When a multilingual crew member switches between languages, personality changes occur. As you can see, there is a significant difference between me speaking Japanese and me speaking English. The same thing can happen to a crew member. The crew member's body language and facial expressions may change. This occurs when crew members adapt their personalities to the cultural norms of a particular language. Another phenomenon is foreign language anxiety. Depending on personality, gender, emotional intelligence, and learning preferences, crew members may feel anxious when languages are spoken. With these roadblocks in mind, we developed the ASM Foreign Language Program. We established that a uniform classroom environment will not be effective. Our plan is for crew members to be grouped together with people who have similar psychologies and learning styles. The program will require learning the English language or another major language. Conversational settings and learning preferences will minimize foreign language anxiety, allowing crew members to achieve foreign language fluency and creating crew unity. When the ASM Mercury-class spacecrafts approach the apoapsis of the transfer orbit, they will make an inclination change to match the orbital inclination of 16 Psyche. This will occur where the velocity of the spacecraft is the lowest. The lower velocity will minimize the amount of fuel needed for change. Retrograde apoapsis burns will place the Mercury transports into orbit around 16 Psyche. Our teammate Jackson Flegel calculated a retrograde burn of approximately 14 kilometers per second. Now that we arrived at 16 Psyche, it's time to construct the ASM Venus by recycling one Mercury transport and harvesting resources from the asteroid. Austin Pham will describe the ASM Venus.
Hi, my name is Austin. Our first and foremost goal of the ASM Venus project is to ground each aspect of the space settlement in reality. This extends to power generation, external structure, and internal design. Power will be generated by nuclear energy rather than solar. We estimate that a total of 4.057 gigawatt hours of power is needed to provide a habitable environment, grow crops, and sustain the population. Because of the inverse square law, the sun is so dim that at least 64 million square meters of solar panels will be needed. With nuclear energy, a total of 34 kilograms of uranium fuel rods will be consumed every year, a far cry from the millions of tons of solar panels required. To reduce the weight and cost of the ASM Venus, we optimize the design of the space element for the most living area to the least surface area exposed to space. We found that a thin cylinder would be the most efficient design, with the ideal measurements being a 64-meter radius and a 2.5-kilometer height. Compared to a Stanford torus adjusted for population, the ASM Venus is 5 times more compact. We were curious about how a thin cylinder could be stabilized, so we conducted a test using TOPS. We found that extending mass from the center of the spin axis increased angular momentum. Weights placed on the ends of spokes extending from the midpoint of the space element store the angular momentum, making it harder for any disturbances to cause major shifts in the life-preserving spin. This spoke and weight system allows us to increase stability without spinning the space element faster, which would affect onboard gravity. Because of the long cylindrical shape of the space element, the interior of the ASM Venus must have a reinforced structure. This is essential since the centrifugal forces will place a substantial amount of stress on the exterior walls. We wanted a repeating pattern to save space, and this limited us to hexagons, squares, and triangles. Of these three, the hexagon is by far the most stable and stress resistant, and hexagonal apartment blocks can be stacked. We often forget about the importance of mundane necessities like clean air. The dangers of heavy gases is alarming, considering that due to centrifugal forces from generating artificial gravity, they will drift towards the floor of the space element and could suffocate small children. The ASM Venus will open vents in apartment floors when gas detectors detect the presence of heavy gases. Artificial gravity will force these heavy gases through the vents. The 3 phases that we have outlined, the preparatory low Earth orbit phase, the transportation phase, and the final construction phase, develop a vision for the future. A future where that admittedly requires great bravery and persistence. A future where humankind has found a place among the stars. Mahalo nui loa, and a special thanks to our advisor, Frederick Herman, to our co-advisor, Christian Williams, to Lynn Zielinski for coaching us through this presentation, and to the National Space Society for giving us this opportunity. Thank you very much for listening.
Congratulations to the Aerospace Meridian team. Thank you so much on behalf of the National Space Society and from Al Globus, who is the founder of the Space Settlement Contest, and his advisor help, Matthew Levine, who I know have ecstatically loved your project and your presentation. So thank you, everybody. You did a great job.
Yeah,
Thank you so much.
you.
Thank you.
Thank you.
Thank you.
National Space Society is proud of you. You have a great career in whatever you do.